Okay, so this video is going to outline the evidence that uncovered some pretty major problems with the Plum Pudding model of the atom and led to a nuclear model of the atom. We'll use this new model to account for the fact that the masses of the atoms we knew, when placed in order, did not rise in even steps, and we're going to use symbols and words like isotope to explain why some elements do not appear to have a whole number atomic mass. The Plum Pudding model, or the Thomson model of the atom, was proposed in 1904 in response to Thomson's discovery of the electron. This described an atom as behaving like a positively charged ball, or pudding, or perhaps you could think of it like a muffin, which was stuffed with negatively charged electrons like fruit in a pudding. It was only 5 years later, though, that a major weakness was found with this model. Since the end of the century, scientists had been investigating something that at the time was very new and exciting: radioactivity. They found that certain minerals seemed to be releasing highly energetic particles that could pass through materials that light could not. And this gave early X-ray-like images and caused some of these materials even to be warm to the touch. People thought these materials must have had special life-giving properties, and they went totally crazy over them. They even put some of them into beauty products. No, really, they did. A scientist called Ernest Rutherford was working in Manchester around this time and was really interested in this radioactivity. One type of radioactivity contains high-energy particles called alpha radiation. We knew at the time that these particles carried a 2+ charge and were the same weight as a helium atom. Rutherford was interested in looking at what would happen with these particles on a very thin sheet of material. One of the properties of gold makes it extremely useful for this purpose. It can be hammered into incredibly thin thicknesses. I mean, like millionths of a meter kind of thin. Now this seems like an odd thing to do because we'd already seen alpha radiation smashing through far thicker materials without being stopped. He instructed two scientists who worked with him, Hans Geiger and Ernest Marsden, to fire alpha particles at this sheet of extremely thin gold foil and measure the rate at which they came through. Now Geiger had yet to invent his famous Geiger counter for measuring radiation, so Marsden had to use a special piece of material that made an instantaneous glowing spot when it was struck by a particle. Unsurprisingly, the particles seemed to be coming through as expected. When the measuring device was moved to other angles as well, it looked like some of the particles were being deflected, but this agreed with what we would expect. Let's think about what was happening in terms of the Plum Pudding model. The atom had a very spread out positive charge, occupying the whole size of the atom, with little bits of negative charge stuck in here and there. For simplicity, we'll ignore the electrons and just focus on that positive charge. As one positively charged particle comes close to another, it might be hard to imagine what will happen, so we can use another type of field that we are more familiar with: gravity. Think of the alpha particle being like a marble. This marble is moving at great speed over a rubber sheet. When the sheet is flat, then the marble will just go straight over it. Let's imagine now that the sheet is modelling the positive charge in an atom. The Plum Pudding model tells us that the charge is very spread out, and the charge is going to push away the alpha particle. We can model this by thinking of a sheet that's been pushed up a little bit in the middle. The sheet slopes away from the middle of the atom, but it's very shallow. If it's not obvious from my lame drawing, imagine stretching a balloon out and poking your finger up from underneath to make a shallow lump. If we run marbles over this sheet at great speed, again most will go straight over it, but they may also be deflected a little. None of them are going to be diverted from their path very much, unless, for example, we were able to slow them down really slowly, then perhaps they might be deflected by a larger amount. But fast-moving marbles are going to go straight through this pretty much. Now Rutherford suggested that it might be worth taking a look on the same side of the gold foil as the source of the particles, to see if any were coming back. This was totally crazy, because there's no way anyone was expecting any of these particles to come back, just in the same way that none of the marbles fired over our shallow, undulating rubber sheet are going to come straight back. they're moving way too fast to be deflected that much. Sure enough though, every now and then, and I mean Marsden had to wait ages to see this, a particle did return. What did this mean? Well, if we go back to the imaginary rubber sheet and the marbles, the only way to get a marble to come back is if, instead of being a very shallow sheet with a lump, okay, and spread out, this lump was sort of spread out all over the sheet, the lump must be extremely steep and pointy, but in a very small part of the sheet. That way, most of the marbles would still fly straight over the sheet. But if a marble comes at it nearly straight on, it could deflect that marble back. Now the gold foil was so thin that the particles could only be deflected by a very small number of atoms before they emerged out the other side. That meant that the positive charge in the center of the atom must be very highly concentrated, like in our last rubber sheet analogy. After doing further experiments, it was shown that in reality, all of the positive charge and mass of the atom was contained in a very small bundle of particles, which would later be called the nucleus. Meanwhile, the electrons orbited this nucleus like planets in the solar system. This nucleus was seriously small. So small, in fact, that if a football was the size of the nucleus, the first electron would be around 3 kilometers away. The vast majority of the atom was just empty space. Rutherford did other experiments with radioactivity and suggested that this nucleus contained particles, called protons, which have a positive charge. A hydrogen atom, for example, would have one proton in the center with a positive charge and an electron orbiting around it. All atoms have to be neutral, remember, so there will always be the same number of electrons as there are protons. Each atom is so light that it makes sense to just measure their masses relative to each other. Let's call 1.67 times 10 to the minus 27 kilograms one atomic mass unit. A proton would therefore weigh 1 mass unit, and an electron would be so light, an 1800th of a mass unit, that we can effectively ignore its mass altogether. According to Rutherford's theory, the next lightest element would have 2 protons and 2 electrons. We would expect it to weigh 2 mass units, therefore, twice as much. But we ran into another problem. In actual fact, helium weighed 4 mass units, 4 times as much as a hydrogen atom. It was much later that a scientist called James Chadwick found that there was another particle in the nucleus which had no charge but the same mass as a proton. He was able to show this by firing alpha particles at a sample of beryllium. The alpha particles were absorbed, but a strange emission was coming out from the beryllium that wasn't deflected by a magnetic field at all. This meant it had no charge, and it also meant that there was no way we could measure its mass by bending the stream of particles like Thomson did. Instead, Chadwick smashed this new stream of particles into another material, paraffin wax. The particles smashed into the nuclei in the paraffin sample and knocked out protons, which could themselves be measured. In the same way that you could find out about the speed and mass, the momentum, of the white ball in snooker by measuring the speed and mass of the ball it hit, Chadwick was able to determine that this neutral particle had the same mass as a proton, and as such it was named the neutron to reflect its neutral charge. Scientists around the world were seriously excited, and it's no wonder they were so happy. We now had everything we needed to start building up the internal structure of the atom. Helium had 2 protons and 2 electrons, and because it weighed 4 times as much as hydrogen, it must have 2 neutrons. Lithium was the next heaviest element. It weighed 7 times as much as hydrogen, but its nucleus was only 3 times as positively charged. That meant it had to have 3 protons and 3 electrons to match, with another 4 neutrons to make it up to 7 mass units. You can practice adding particles up to make an atom over on the PhET website at the University of Colorado. I'll leave a link to the activity here. We use symbols to help us keep track of the particles in the nucleus. When we write helium, for example, we write 42He. The smaller number is the number of protons in the nucleus. It's sometimes called the proton number and sometimes called the atomic number. Whatever way you look at it, the smallest number of the two will define what element you have. Atomic number 2 is always helium. The larger number is known as the mass number. In some places you'll see people write it in top, and in other places you'll see them write it underneath. Just look for the largest number. I write it in this arrangement. This mass number tells us the number of protons and neutrons available in the nucleus, and because they are the same relative mass, we can simply take the larger number from the smaller number to calculate the number of neutrons. In this case, 4 take away 2 leaves us with 2. In the case of 7,3 lithium, we have 3 protons and, as always, an equal number of electrons for the atom, and so we have 7 minus 3 equals 4 neutrons. Let's look at one more example, which is chlorine. Chlorine comes in 2 flavors, known as isotopes, which have the same atomic number but a different mass number. In other words, they have the same number of protons but a different number of neutrons. Chlorine 35, written 3517Cl, has 17 protons, and 35 take away 17 leaves us with 18 neutrons. Chlorine 37 has 37 minus 17, leaving us with 20 neutrons. In terms of their chemistry, these two atoms will behave identically. The electrons are only affected by the protons in the nucleus. The neutrons, having no charge, don't interact with the electrons at all. The only effect that different isotopes have is on the physical properties of a substance, like its melting point or the speed at which it diffuses. This is because heavier particles will need more energy to get them moving at the same speed than lighter particles will. A machine called a mass spectrometer allows us to weigh atoms incredibly accurately. One of the most common modern types of machine acts a bit like a drag race, where 2 cars have to race each other in a straight line over a short distance. The person whose car can accelerate the fastest tends to win. The particles to be measured are ionized by knocking electrons off them so that they can be accelerated by an electric field, and then they're allowed to move through a tube in the machine like a kind of racetrack. This tube has had all of the air sucked out of it to stop our particles crashing into air particles and ruining the experiment. If all our particles are given the same push, then the lightest ones arrive at fastest at the other end. This is just like you would expect an empty van would be to a fully laden van in a drag race if they were both running with the same type of engine. Because the machine measures how long it takes the particles to move through it, it's called a time of flight mass spectrometer. There are other types of mass spectrometer too that use magnets to bend the path of the moving ions. Let's look at some examples of results from this experiment. The bottom axis shows the mass-to-charge ratio, usually given the symbol m/z. It's easier for the moment if we imagine that all our ions only have a single positive charge, so when we see a line appearing on this graph, that will tell us the mass of that particle. The y-axis tells us how often we see these particles. A high number means that there are many particles with that mass. Let's imagine we can do the experiment just with 100 atoms of bromine. In reality, we'd do it with a lot more than this, but I'm choosing this number to make things a little bit easier for us later on. We'll feed the atoms in, make sure that they're in the gas phase, and ionize them by bombarding them with high-energy electrons. We accelerate them down the track by repelling them away from a negatively charged electric plate towards a positively charged one. The lightest ones move the fastest and arrive at the detector first. This detector is able to identify the arrival of an ion because, as a particle with a charge lands on it, there'll be a small electric current generated, which can be amplified and communicated to a computer for analysis. The more ions that arrive at a given time, the higher that current will be. So the results are in from the experiment, and we see that there are two peaks. This tells us that there are two types of atom, two isotopes. One of these peaks occurs at a mass of 79 atomic mass units, and the other one at 81. If we assume we have 100 atoms in total, then 50 of them were bromine 79 and 50 of them were bromine 80. What do you think would be the average mass of a bromine atom? When we look at the periodic table, it tells us that the average mass of a bromine atom is 80, because we have two isotopes and their masses average out to be 80, because there's an equal number of each. We'll look back at chlorine now. We repeat the experiment and we get a graph that looks like this. Out of 100 atoms, 75 of them weighed 35, and 25 of them weighed 37. If we add up all of the masses of the atoms, that's 75 lots of 35 and 25 lots of 37, and we divide this total by the total number of atoms, 100, we get an average mass of 35.5. So when you see a non-integer, that's a non-whole number value on a periodic table, it's really telling you that there are a number of isotopes and they don't exist in equal proportions to each other. So to wrap up, we've seen that Rutherford and later Chadwick provided some evidence that suggested that the Thomson model of the atom was incomplete. We discovered that the atom has a nucleus and that this nucleus contains particles called protons and neutrons with the same mass as each other, each one about 2,000 times as heavy as an electron. Because the electrons are so light, we don't use these when we're considering the mass of an atom. And we've used symbols to identify elements and the numbers of protons and neutrons within them.